So in this question, we have to show that that function is an increasing function, which means it goes up and up and up. So if we think of any increasing function, we know that this one will either look like that or like that, because it's a positive x cubed. But in fact, any function that keeps going up has a particular characteristic, which is that at any point the gradient must be positive. So we can see all the way along the gradient's positive. So in fact, what we're showing in this question is that we have this type of cubic shape. Now, we don't have to worry about the shape, because we can show that the cubic is that shape by showing that the derivative, which is the gradient, the first derivative, is positive for all values of x. So we could do this question just by saying that if f of x is x cubed minus 6x squared plus 13x minus 7, then f dashed of x, and note that if f of x equals y, then f dashed of x just means dy by dx, which is the more familiar way that you'll have seen the derivative. So that is 3x squared minus 6 times 2x plus 13, which is 3x squared minus 12x plus 13. Now, we've got a quadratic, so that's going to look, it's a positive quadratic, so it's going to look something like that, and we need it to be greater than 0. So there's two ways we can do this. First of all, we could do completing the square, and that will give us, we can say that f dash of x will be 3 times x squared minus 4x plus 13, and that is going to be 3 times, remember when we complete the square we halve the coefficient of x, and then we have to take away that 2 there squared, which would be an extra bit. And if you're at all uncertain about completing the square, there's an explanation of it in question 5 of the FMSP3 videos in this playlist. Anyway, we've done that bit, so then we've still got our plus 13. And when we get rid of the outer bracket, that gives us 3 times x minus 2 squared minus 2 squared is 4 times the 3 is 12 plus 13, which is 3 times x minus 2 squared plus 1. And since the squared bit here has a minimum value of 0, then the whole thing has a minimum value of 1. And so we can say that f dashed of x is greater than or equal to 1, and we can conclude from that that f of x is an increasing function. Now, the alternative way of doing this, because we're looking at a quadratic curve, which you can see in green there, all we have to do is to establish that it has no real roots. So, to do that, we can look at the discriminant. We know that for no real roots, the discriminant has to be negative, so that when we try to square root it, we can't in the real numbers. So, the discriminant for f dashed of x, we would have, if we put our a, b, c there in green, then we have the discriminant, which is b squared minus 4ac, will be minus 12 squared, take away 4 times 3 times 13, And that is actually 12 squared, take away 12 times 13, which means we can see without even finishing working it out, this is going to be less than 0. Now, because it's a positive quadratic, that means that if it doesn't have any roots, then the axis must be below the minimum, and therefore we've shown that it's positive. But because we're not allowed to think about the shape in that way, what we need to do is just show that for some value, so we could put 0 in, then because one value is greater than 0, that means that those two facts together tell us that f dash of x is greater than 0 for all values of x. That upside down A, it means for all. And again, we can then say, therefore, f of x is increasing.
This question is about an increasing function, and we also get decreasing functions, which are the other way up. So they are going down all the time, and therefore their derivative is less than 0 for all values of x. So we'll have a quick look at some increasing functions. This first one that you can see on the screen is the one from the question, and we can see that indeed it has that particular cubic shape that doesn't have a maximum or a minimum. Think about what's the simplest increasing function you know about. Well, it's a straight line. Up and up and up it goes, and its derivative is the same at all points. And so as long as it has a positive derivative, it will be an increasing function. Incidentally, increasing and decreasing functions are called monotonic functions. So that's a nice little word for you if you haven't heard it before. Well, quite a big word, monotonic, 4 syllables. Another one you've come across is the exponential curves. So this one is e to the power of x, but in fact any positive greater than 1 will give us an increasing function. So let's have a look at that. We'll take away e to the x and put in a slider, which I'll put at 1 to start with. And so that's a to the power of x. And if we slide that up from 1, up it goes. If we go below 1, it becomes a decreasing function, and then it doesn't mean anything for negative numbers. Okay, now related to e to the x, which I'll pop back on, get rid of that one, we have log x, and that's an increasing function as well. If you think about the derivative of log x, which you won't necessarily have come across yet if you haven't done A2 maths, but you will come to it. And in fact the derivative of log x is 1 over x, which is a positive function for all positive x, and of course log is only defined for positive x in the real numbers. So the next one I want to look at is, at first sight, not an increasing function. So this is one of the commonest functions you've dealt with, a quadratic, x minus 2 squared minus 3. So x minus 2 means that the symmetry and the minimum are at plus 2, and the minus 3 tells us that the minimum value of the function is minus 3. And of course that's going down and then up, but you'll notice that half of it is increasing. So once we get past the minimum, it's then increasing forever. And you'll find out in A2 that we can have functions defined with a domain, and the domain restricts which values the function applies to. So I'll pop that on now there, and the writing's a bit smaller because I'm not sure how to make it big like that. Might find out one day, maybe you can't. But anyway, the point is, we're saying put in this function, which is the same as the original one, of course, and we can sort of see it is because it's right on top of it, but only for x between 2 and 10 inclusive. Inclusive meaning it includes the end values. So we can't see the other end, the 10, because we're not going up that high. But if we get rid of the original full curve, we can see that if we restrict the domain like that, then we do indeed get an increasing function. Okay, now there's another one that's quite nice, which again you've come across, and that's tan x. And we can see that it looks like tan x is increasing at every point. If we take any one of these branches, then it's increasing all the way. But we can't call it an increasing function because we have, for example, that the function applied to 1 is greater than the function applied to 3, and so there isn't an increase between x equals 1 and x equals 3, for example. But we can do to this what we did to the quadratic a moment ago, and we can restrict the function to between minus pi by 2, which is again something you'll come across in A2. Pi by 2 is actually 90, so that's between minus 90 and plus 90, and then indeed we do get an increasing function. So some functions come increasing, like that sort of cubic and a straight line and e to the x and log x, but some have to be restricted, like a quadratic or indeed a tan function, which you can still see on the screen. If I take away the repeating tan, then we can see the tan in blue there. There we are. So that's increasing functions.